Hi, this is Nastanowski, and we're going through Monoidal category theory, the book, and we're finishing chapter 4 today. And let's just remember what chapter 4 was about. It was about relationships between categories, and the main central idea in chapter 4 and in the rest of the book is this adjoint functors. So we use a lot of adjoint functors right here. So this is going to be a mini course on categorical logic. Okay, and so we're going to discuss lots of different aspects of categorical logic and go through that. I want to say, so basically what we're doing is we're looking at logic, which is an ancient field, through the lens of category theory. And it's particularly elegant. It's extremely elegant. And the idea is as follows. All the operations in logic are basically types of functors, which have certain relationships with each other, and mostly it's a form of a lot of exercises in adjoint functors. You can see where adjoint functors show their face all over, and so that's very interesting. Okay, just want to say, for the most part, this stuff was done by William Levere in the 1960s and 1970s. That's one side thing. And the other side thing I want to say is, when you hear the phrase categorical logic, it means a lot of different things to a lot of different people. Okay? And so a lot of people will say, oh, why don't you include this, why don't you include that? Well, I can't include everything here, and a lot of things are included elsewhere in the book. You'll see that later on. But this is just pure logic. And so we're going to deal with ands and ors and arrows and quantifiers and stuff like that. Anyways, I really have to say, it's a very pretty section. It's a very pretty part of category theory, because you'll see it's simply elegant. I can't describe it in any ways. You have a functor, you show what the functor satisfies, and you show relationships between the functors. It's extremely nice, and it's all logic. Okay, so one more thing. Logic comes in two forms. Predicate, propositional logic, which is about a thing, and predicate logic, which is about many things. So we're going to first do propositional logic, and then we'll build on to predicate logic. Okay, so propositional logic deals with a category which we've seen before, namely prop. Okay, so let's go through this. The objects are propositions, which are statements that are true or false. Okay, and here's a typical statement that's true or false. Here's another typical statement that's true or false. And there is an arrow. There's at most one arrow between any two objects. It's called a thin category. There's at most one object between any two. There's at most one arrow between any two objects. There's either no arrows or one arrows. But if P implies Q, then there's an arrow. Okay, between them. Okay. So this is a category. Identity, every object implies itself. If P implies Q and Q implies S, then P implies S. That's composition, etc. We've seen this category before. We've worked with this category before, and it's a pre-order. Okay? Okay, which means one thing can imply the other thing, and P can imply Q and Q can imply P, or there's an arrow from P to Q and there's an arrow from Q to P, but it doesn't necessarily mean that they're equal. So that's a pre-order. Okay, so now that we have this category and we deal with this category, let's talk about different functors that relate this category to, well, in this case it's going to be itself. So there's a functor which goes by the name conjunction or and basically what it does is it takes a proposition and it takes another proposition, okay, and it outputs a proposition. Okay. Okay, so this functor is the and functor. So it takes one thing, so you could say I like ketchup, and you have another proposition, I like mustard, so then you can have I like ketchup and mustard. As nice as it gets. Okay, it's covariant They're both covariant. I just want to show you what the functoriality is of this thing. But it basically says that if P implies Q and P prime implies Q prime, in other words, if this arrow is in here and this arrow is in here, then P and P prime, P and P prime implies Q and Q prime. So if this implies this and this implies this, then if you have both assumptions, then you get both conclusions. So that's very simple. Okay. The shocking thing is, no, I'm sorry, the not shocking, but the interesting thing is the and is the product. So this is also a product. This is a product. So I have a nice example to show you that. Okay. So in the book I have this cute example, and it's a common theme throughout the examples. Okay. So here's a statement: Jack will be able to learn a lot of, I'm going to start with physics. Okay, Jack will be able to learn a lot of math. Here's two logical statements, and what we can do is as follows: Jack will be able to learn a lot of math, and whoops, I'm going to stress that. So we want to stress that. And physics. I'm sorry, it's a little bit close to each other, but that's okay. Okay, main point is, if Jack will be able to learn a lot of math and physics, that means Jack will be able to learn a lot of physics, and it means Jack will be able to learn a lot of math. So those are projection functions from this AND operation. Okay, if you can do both things, and you can do this and you can do that. But more importantly, it satisfies the universal property of being a product, which means as follows: if you have something that implies both of them, for example, Jack is learning, oh, I'm sorry, maybe you have a nose. Jack is studying category theory. Studying category theory. Okay, well, if you're studying category theory, that implies that you'll be able to learn a lot of physics. Okay, and if Jack is studying category theory, that implies that Jack will be able to learn a lot of math. And the universal property says, if this is true and this is true, in other words, if this satisfies this requirement and this satisfies this requirement, then it satisfies the AND of it. So we have it like that. Okay, now just want to show it in terms of without symbols. So it goes as follows. I'm sorry, without words. So if P stands for one thing, Q stands for another thing, then you have P and Q, and you have the projection functions. P and Q implies P, P and Q implies Q, okay? And furthermore, if you have another statement S, and S implies P, and S implies Q, that implies that S implies P and Q. Okay, so what we see is the AND is nothing more than the product, Cartesian product in the category. Okay, very nice. Okay, it's the product in the category. Okay, I'd like to show you the universal properties of the product, although we saw this back in chapter 3, but I'd like to see it again because it's very pretty and it's worth reminding anyways. So that's very nice. That's a cute little example. It's very nice, but let's just see what universal properties it satisfies here. Let's keep this in mind. It says as follows. It says hom in prop, that's here, okay, of S to P and Q. If there's a map from S to P and Q, that means, okay, that hom prop, there's a map from S to P, and there's a map from hom prop S to Q. Okay. So what does this say? Let's just stare at it for a second. What does it say? What it says is that if there's a map from here to there, that means this has a map and this has a map. Okay, so this is not empty and this is not empty. So the other way is if this is not empty and this is not empty, so this is either these are pre-order categories. This is either 0 or 1 objects. If this has 1 object and this has 1 object, then this has 1 object. Okay. So that's just restating the definition of a product in the category of props. Okay, but hold on, let's just restate it again. So this is the same thing as saying hom prop of S, comma, P and Q. This is the same thing as hom prop squared. So let's just remember what that means. That's a product of 2 categories. It's a product of 2 categories. And what we're doing is, both of these come from S, so it's going to be S, comma, S, and the other pair is P, comma, Q. So in this double category, if you have a map from S to P and you have a map from S to Q, then you'll have a map from S to P and Q. Hold on. Let's just rewrite this again. This totally makes sense, but we can also write this like this. Delta S. Okay, and that is that the diagonal map from prop to prop squared. Okay, so what we see from this is, hey, that's on the right, that's to the left. So what we see is, and again, we've seen this before. So this becomes, ready? There's a map from prop to prop squared called delta, okay? And what this is on the right, that's on the left, so the end, oops, the end is there, and it's a right adjoint to that. Okay, that's very pretty. So that's a right adjoint. So that's our first result. The AND is not just a functor that takes propositions to propositions, but it satisfies a universal property, namely, it's the product. So that's very nice. Okay, great. That is the first operation. We're going to see lots more operations in a second. Okay, sorry about that. Okay, the next operation is called, its symbol is this, okay? It goes from prop to, takes 2 propositions and outputs a prop, but it's contravariant in the first step. It's contravariant in the first thing, okay? And this has different names. for the category theorist, this is going to be called the internal HOM. You'll see why it's going to be called the internal HOM in a second, okay? But for the logician, it's called logical implication. Okay, and so it goes as follows. It says P logically implies Q. Okay, I have a lot of cute examples of this in the book. Let me just go through this one. If Jordan understands category theory, Jordan will see the world in a new light. It's cute. Okay, next. It is raining implies there are clouds in the sky. So each one of these is a proposition by itself, but this arrow is an if-then statement. So if Jordan learns category theory, then he will see the world in a new light. If it's raining, then there are clouds in the sky. If you drive more than 50 miles an hour, you will get a ticket. Okay? And if the moon is made out of green cheese, then the sky is blue. Okay? By the way, those have nothing to do with each other. The moon being made out of green cheese and the sky is blue really has nothing to do with each other, although they're both in the sky. But the main point is, because the sky is blue, this is always true. Okay, so no, it's not the main point, but you can take any two propositions and you can make this new proposition out of it. What I'd like to do is I'd like to show you how it's covariant or contravariant depending on this. So it goes as follows. Let's do it here. If Q implies Q prime, then I want to show this. P arrow Q implies P arrow Q prime. Okay, what this shows, that's the functoriality along the second operation. Q implies Q prime. Let's just see why it works in English. If P implies Q and Q implies Q prime, then P implies Q prime. Okay, it's also contravariant in this thing. So let's do this. If P implies P prime, okay, and now we're just going to look at one Q, and so we get as follows: P arrow Q. Oh, I think I got this the wrong way. P imply. Okay, arrow that implies P double arrow Q. Let's see why this is true, what this is about. This says, if P prime implies Q, then because you know that P implies P prime, so you're going to have P implies P prime implies Q, then you're going to have P implies Q. Okay, so that's contravariant in the first variable. That's what it shows. But by the way, you can do both of these in one shot. Let's just erase this and erase this. Okay, and we can do both of these in one shot. And we say the functoriality of this thing basically says P prime implies double arrow Q implies P double arrow Q prime. Just see why it's true. Okay, let's assume this, and this. Q implies Q prime, P implies P prime. P prime implies Q, so this implies this. Well, let's put it like that. Sorry, double arrow. No, sorry. What in Linkabook. That's a P prime. That implies this. So if P implies P prime and P prime implies Q, then P implies Q prime. So that's that. Okay, but it's important to keep distinction between this arrow and this arrow. Let's go through what this is. This is a logical operation which corresponds to a functor between categories. Okay, here's one category, here's another category. This is this is a functor between categories. This is a morphism within the category. The point is you can internalize this morphism this way, and so that's why it's called an internal hom, because it's coming into that. It's doing it. Okay, well, let me show you the relationship. What's this relationship between, what's this internal hom about? Okay. In order to do this, we have to go back and remember some things from chapter 1, all about sets. Okay, goes as follows. Okay. Again, we've seen this before. We saw it before in chapter 4 also, but let's just review it. Let's just remember it. Let's say you have a set S and you have a set T, then you could look at S cross T, okay? And you could talk about functions from S cross T to U. Very nice, okay? You could also look at S to hom, this is all in the category of sets, of T to U. Okay, and what we said was these two, the set of functions here, are isomorphic. Okay, another way of saying that is, you ready? Okay. That is on the left side, so we write it like this. This is left adjoint to this. Okay. So both, this is a functor from set to set, this is a functor from set to set, covariant. You have two functors from set to set. I think we call this left of B, R sub B, and I think we call this right of T or something like that. Well, guess what? That's about sets. There is an image of this over here, and it goes as follows. You ready? So this is about logic. P and Q arrow S is logically, well, I'll explain to you what that is in a second. You know what? Let's not do logically. Let's write it out. This is true if and only if, ready? P implies Q imply double arrow S. Let's just see why this is true in terms of English. If P and Q are true implies S is true, then if P is true, then Q also, then you have, if Q is true, then you know that P is true, then P and Q implies, and then you're going to get S. Okay, great. Okay. But I want to show this, so now I want to say, oh, so anyways, this is called the internal hom. Comes from this word hom, so this is kind of the internal hom. It's a functor from the category to itself. It's covariant in one thing. Okay, so what we get is as follows. You have the category prop. You have the category prop again. Okay, we did this before for sets. I can show you this adjunction for sets. We had this set, okay, and I think it goes like this, cross T, and this is T, hom, T, comma blank. Okay. Okay, anyways. Take a Q, so this is P and Q, okay, and now I'm going to do this, Q arrow, anything else, okay? So you have, this is a functor that takes a proposition and gives you and it to Q. This is a functor, internal hom with Q, okay? And now we have, this is left adjoint to that, just like this. This is left adjoint to that. Now, in some sense, Notice these are regular categories. I shouldn't say the word regular. These are categories where you can have more than one object, more than one morphisms between two objects. This is a category where you can have at most one object between two, at most one arrow between two objects. So in some sense, this is a shadow of this, but it's a statement about logic, and it's a very nice statement about logic. Okay, what I'd like to do is go through what the unit and the co-unit of this is. So the unit, it says as follows. Okay, you can work it out. It goes P arrow, Q double arrow, P and Q. Okay. Okay. What you first do is take the and, do P of it, then take that and do Q of that. Okay. And you start off with the identity. So basically is as follows. What this is the unit. So it says if you know P, and that implies that if you know Q, then you know P and Q. Okay. That's nice. Doesn't say anything shocking. The co-unit is something a little bit more well known, and this is as follows: P and Q, and I'll just write it out the way I wrote it. Q implies P. No, that's not what it is. Sorry. P arrow Q and P. I'm sorry. Nope. Sorry. You got to keep the, I mean, what I said was right, but you just have to keep the variable straight. You ready? It's Q double arrow P. Q double arrow P and Q. Sorry. Q. It's getting frustrating. Q double arrow P and Q implies P. Okay. Now this is known by a famous statement. It's called modus ponens. Modus is modus operandi. Ponens is pushing. So you're pushing forward. If you know Q and P, and you know Q, then you know P. Okay. Okay, great. Let's go further. So lots of different operations here. Let's just see. So far we had two operations. We had an and internal hum, or an and logical implication. Okay, but now let's do some more operations. So this is called disjunction, or. It takes a proposition and a proposition, and it outputs a proposition. Okay. Just want to show you why it's functoriality. So if you have P implies P prime here, and you have Q implies Q prime here, then P or Q implies P prime or Q prime. Okay, that follows from functoriality, and it's logical. If this implies this, then one or the other is going to imply one of the other. Okay? I have a nice example of this one also. Okay, it's on page 212, very cute example. Jill, so before we talked about Jack, here we can talk about Jill. Jill plays music. Jill studies category theory. Jill studies category theory. Okay, and we can now make two inclusions. Okay, and it goes as follows. Jill plays music, or, stressing the word or, Jill, or studies category theory, studies category theory. Okay, so if Jill plays music, then it's true that Jill plays music or studies category theory. If Jill studies category theory, then Jill plays music or studies category theory. And then, right, so one of them is true. Okay, great. Now, Jill is happy. That goes here. That goes here. If Jill plays music, Jill is happy. If Jill studies category theory, Jill is happy. Conclusion, Jill plays music or studies category implies Jill is happy. Which means, you ready? Or is the coproduct. Satisfies this universal property, or is the coproduct. Okay, so we had a disjoint union. Now we had the product, now we have the coproduct. Okay, great. Okay, now I can do again the same type of thing, satisfying universal properties, etc., showing the map, one map or the other map. Okay, but the main thing is as follows. Let's put it all together. We've seen this diagram before when we were talking about products and coproducts. Here's the category of prop. Here's the category of pairs of propositions. And there's the codiagonal map. Takes everything to its codiagonal. We already saw that and is a right adjoint to that. And what I just showed was, or not, what I just talked about was, or is a left adjoint of this. And we saw this before. We saw it about limits and co-limits. We saw it about initial objects and co-initial objects, and terminal objects, etc. So it's a very neat way of seeing ands and ors. Okay, great. More operations. More operations. Okay, so there's another operation called a by implication. It's basically another way of saying if and only if, and it goes as follows. P by implies Q. It means it implies this way and this way. If and only if P arrow Q and Q arrow P. So when both this is true, when both this happens and this happens, we can write it like that. Okay, we'll see that this is, so that's some by implication. Okay, great. Another operation, not, which goes from propositions to propositions. Okay. Okay, but I have to fix this in a second. Let me just to give you an example. The proposition, I like ketchup, not of that is I don't like ketchup. Okay, the only thing is this is an opposite category. It goes in the opposite sense. Let me explain to you what that means. That means if P implies Q, then functoriality of this gives you as follows. I'll just write it the way. Okay, that implies that not Q implies not P. Okay. If P implies Q, then if Q is false, then P is also false. Because if P was true, then we'd have P is true. Okay, so you get this contravariant functor. Very nice. Okay. Now, again, not goes from prop opposite to prop, or so prop opposite to prop, or prop to prop opposite. Okay, and we're going to deal with two types of systems now. Okay, now question: what's the relationship between not and not? So we're going to deal with two types of systems now. Intuitionistic. What that basically says is not is left adjoint to not, or right adjoint, doesn't matter. They're self-adjoint in some sense. They're self-adjoint functors. So that's an intuitionistic thing. Okay, but let me just say what the unit in this thing is. If in this adjunction, we could talk, so that would be something like this. So the unit is P arrow, not P. So take the identity, go once, twice, not P. Okay, that's the same thing as saying not P to P in prop opposite. But let's just deal with prop. Okay, so that's the intuitionistic in that. We don't say that they're equal. We say it like this. So this is one type of system that we're going to deal with, intuitionistic system. But there's a stronger system that we're going to deal with also, which basically says it's an equivalence, okay? And so Boolean, so not is its own inverse. So Boolean systems have the following thing: not P is isomorphic to P. But how do we say isomorphic in terms of inside the category? We say like this, by implication P. So that's a Boolean system. Okay, so sometimes we're going to deal with an intuitionistic system, sometimes we're going to deal with a Boolean system. Okay, great. Now, I want to prove two theorems about this. And before I do that, yeah. I want to prove De Morgan's law. I'll show you what it is in a second, but I need the whole board. The main point is the rest of the proofs in this chapter, in this section, follow exactly the same way. So I want to do this very, very carefully, and then you'll see all the other proofs come in 1, 2, 3. Okay, this is called De Morgan's law. It says not P or not Q is the same thing as not P and Q, or not P and not Q is the same thing as not P or Q. Okay. Okay, it's a funny way of saying that not is a homomorphism, but it's changing the operation. Notice here's an or, here's an and, here's an and, here's an or. So it's changing the operation. The proof follows from this diagram. But it's very, very elegant. And it goes as follows. Let's just give you the orientation. Here's prop squared. Okay, this is that adjunction that we talked about. Ors and ands, coproducts, products. Here's the diagonal. Great. Here's the exact same thing, but sorry. Here's the exact same thing, but with the opposite over there. So prop goes to prop squared, but the arrows are going to be inverted. Now, the arrows inverted means that coproducts become products, products become coproducts. So that's this adjunction between them. Okay, great. Now let's go through this. Here we have the not operation, and here we have the not operation. They go between props. And here we have the same thing, but here we have pairs of them. So this is the category prop cross prop. So we're going to have not cross not. And here we have prop cross prop op. We have not cross not. So that goes like this. And we have to, this is only true when you're dealing with Boolean logic. Okay, so Boolean, not necessarily intuitionistic. So De Morgan's rules doesn't necessarily work with Boolean logic. It doesn't work with intuitionistic logic. It works with Boolean. Maybe it works one way or something, but we're not interested in that. We're dealing with now where this is an isomorphism, an equivalence of categories. Not is equal to the identity. Not is isomorphic to the identity, not equal. Not is isomorphic to the identity. Great. What I want to do is I want to look at going from here to here. Okay? So let's do it. You ready? I'm going to take a typical proposition here, P. We're going to go here to the diagonal. So this is going to give me P, comma P. So that's pairs of things. It's going to go like that. Great. Now I'm going to do not of them. So I get not P, comma not P. Very nice. Okay. I could have also done it this way and get not P. And then this diagonal takes it to the same thing, not P, not P. Okay, main point is both of these commute exactly. What they're saying is taking a pair of things and then knotting them is the same thing as taking an object, knotting it, and then pairing it. Okay? The diagonal and the knot are homomorphisms of each other. So there's exactly one map from here to here, which makes these commute. So we're following this, following that, is the same thing as following this, following that. Very nice. Okay, what I'd like to do is, I'd like to look at left adjoints of this functor. Okay? Well, so there's one map like this. I'd like to look at left adjoints of this functor. So let's do that. Okay? So I'm going to erase these things, and I'm going to just draw the left adjoints. Okay. So one thing is go to the left adjoint here. So take a typical pair, P, comma Q. Okay. Okay. And then it's going to go to P. Let's just do it like this. Okay, it's going to go to P or Q. Okay, and then this is going to go to not P or Q. Okay, that's one map. Okay, and that's a left adjoint followed by a left adjoint. By the way, this is an equivalence of categories, but that's fine. An equivalence is a special type of left adjoint. Okay, we could also do it this way. Let's see what this does. This says, look at not P, comma, not Q. Okay, so I have P, comma Q goes to not P, not Q. Okay, and then we look at the left adjoint here. What's the left adjoint? That's that. Here it was over here, but here we flip the arrows because we're dealing with op. So this becomes what? Okay, this becomes, you ready? This becomes not P and not Q. Okay, great. So let's go through this. We have a function from here to here. Okay, and now I'm looking for the left adjoint of this. So here's one left adjoint, here's the other left adjoint. But 1 second, what do we know about left adjoints? They're unique up to isomorphism. which means that there's an isomorphism in between this, which means you have a double arrow here. And that is exactly this rule. That's exactly this. Okay? That's exactly this. That's because we looked at left adjoints of the diagonal. Guess what? We can look at right adjoints of the diagonal too. And we get this. Okay? Main point, set up this diagram perfectly, which shows all the adjunctions. I told you in the beginning that this whole field is all about adjunctions. Okay? It's all about adjoint functors. Okay? So all you have to do is set up your adjoint functors and you get it. Okay, great. Okay. Okay. All the proofs are going to be of a very similar nature. It depends what you set up your functors and you get them. Okay, great. Next, one more topic and we go to predicate logic. The topic is as follows. All this is about the pre-order. Prop is a pre-order. Okay, when we said every pre-order has built inside of it a partial order. Okay, the partial order is called the Lindenbaum category. Lindenbaum category. Let's just remember what a partial order is. A partial order is a pre-order, but we have the further thing, namely, if P implies Q and Q implies P, that means P equals to Q. Okay, anti-symmetry. Okay, and so the way to see this, so this is called the Lindenbaum category. It's written as Lind for Lindenbaum. So this is proposition, this is Lindenbaum. Okay, and the main idea is as follows. Okay, it's if P double arrow Q in this category, then P equals Q in this category. So it's a skeletal category. This is a skeletal category of this. And basically what it says is it just looks at those things where they're actually equal to each other. The propositions are equal to each other. So picks out one isomorphism from all of them. This is a little bit of a stricter category. We're going to need this later on, but that's very nice. Usually logic takes place in here, but sometimes you need that strictification, and we'll talk about that a little bit later on. Actually, we did it already in chapter 3 when we talked about diagonal. So in order to do Gödel, you really need this. Gödel's incompleteness theorem, you really need this. Okay, great. That's the first half of logic. The next thing is called predicate logic. Okay, and what this is talking about sets of things, and you want to know different predicates on sets of things. So I have predicate logic. Okay, I have lots of different cute examples. We'll deal with them in a second. I'm sorry, we'll deal with them right now. It goes as follows. So we have h of x. Okay, and the way to think, first I do some funny ones, then I do some math ones. So h of x, h stands for happy. X is a person, so h of x means x is happy. Okay, and we can talk about h of Bill, and we get Bill is happy. Okay, so we're talking about whether or not a person is happy. Okay, then we have KCT of x. That's again, x is a person, and KCT stands for knows category theory. Okay, knows category theory. If they know category theory or they don't know category theory. Okay, and then we have another one with two variables, mxy. So this stands for, this is a person, this isn't a person, and this says x is a mother of y. If x is the mother of y, then it's true, otherwise it's not true. Okay, those are nice, cute examples. Let's do some more. We have e of n is a number, e of n is whether or not that number is even. So E of 2 is true, E of 3 is false. P of n is if n is a prime number. Okay, G of m comma n. Not only can we have two things, x and y, two people, we can also deal with two numbers. And we say m is greater than n. And the G stands for greater than. M is greater than n. Maybe it's greater than or equal to. Greater, just greater. Okay, one more. A, x, n. So here, again, the things that are talking about, these are called predicates. We have predicates about people. We have predicates about numbers. Okay, the set of things that they're equal to, that they're talking about, is called the domain of discourse. What are we talking about? So the domain of discourse. Okay, let me just tell you what A of x, and here the domain of discourse is a person and a number, and basically the idea is this is true if this person is this number years old. Okay, so that takes care of that. Lots of different things, so lots of different examples, and then I have some cute ways to show you how these operations work, with these predicates. So for example, again, cute, QCT x. If x knows category theory, this is double arrow, h of x, then x is happy. If he knows category theory, he's happy. Okay? Okay, here's another one. If m of x, y, if x is y's mother, and kct of y, and y knows category theory, this implies that h of x. So h of x. So everybody who knows category theory's mother is happy because their child knows category theory. Okay, next. Here's another cute example. If ax m and, oh shoot, hold on. And a y, I think that's n, and m x y. So three things. X is m years old, y is n years old. X is y's mother. X is the mother of y. This implies that G of m comma n. Okay, this is a long statement that basically says your mother is older than you are. By definition. Almost by definition. Your mother's older than you are. Let's just make sure that you got this right. X is m years old, y is n years old, and x is y's mother. That means m is greater than n. Okay. One more example. If E of n implies E, n plus 1. Okay. If n is even, that means n plus 1 is not even. By the way, that's an if and only if statement. Okay, great. So these are cute examples of predicates about people and about numbers, and open up any logic book. There's millions of these, and it's very important to learn how to write things in terms of logic. Very nice. But there's another operation in logic, and it goes as follows. Just want to follow the... Okay. Okay, so there's something called quantifiers. What are quantifiers? They are ways of not talking, if you're talking about predicates talk about many things. So you could talk about all of the many things, or you could talk about some of the many things, or you could talk about exist. So if qxy is a predicate with two variables, I'm not saying what q stands for, but what we can do is as follows. For all x qxy, okay, this will be true if, so this is called a universal quantifier. This will be true if xy is true for every single possible x. So main point is, this is a statement about y. Question, is it true for y that xy for all? So this is true for all x. That's what it is. It's an upside down A. Great. There's another one. Okay. This is called existential quantifier. Existential quantifier. There exists. Okay. This whole statement is true for a particular y if there's some x in here that in the domain of discourse that makes this true. If there's some x in the domain of discourse that makes this true. Okay? Have lots of cute examples in the book, and pays to go through the examples. So let's go through them. It says as follows. For all m, there exists an n such that g of n comma n. Okay, and the way we have to read this is as follows. For all m, the following is true. There exists an n. Oops. Let me just make sure I got this right. For all m. Okay, right. For all m, there exists an n such a g of n. What does it say? Take any m whatsoever. There is some n, okay, such that n is greater than m. Okay, what that basically says is there's an infinite amount of numbers. Take any number whatsoever. There's another number, n. There exists a number that's larger than it. Okay, so that's typical. Okay, let's do another one. There exists an n such that e of n and p of n. Okay, what's that say? There is some number that's both even and a prime. There's exactly one number, but that's okay. That makes this true also. Okay, and that number is 2. 2 is even and it's a prime. Okay, let's do another one. For all n, p of n implies there exists, lots of parentheses here, an m such that g of m comma n and p of n. Okay, let's see what it says. It says, for every n, if n is prime, then there exists an m such that m is bigger than n, and m is prime. Okay, what that says is, if you have a prime, there's a larger number that's also prime. Okay, and that's another way of saying the infinity of primes. There's an infinite number of primes. Okay. One more cute example, and we'll move on. Okay, I'm sorry. We're supposed to not only be teaching categorical logic, we're teaching logic too, but quantifiers are always fun. It says as follows. For all n, p of n, and, P of n plus 2 implies there exists an M such that, sorry, okay. It's a cute statement. It says for all n, if n is a prime and n plus 2 is a prime, such primes that are separated by two numbers are called twin primes. Okay, so obviously except for 2, all the other numbers are odd. So here's an odd number, here's an odd number. So 5 and 7 are an example of twin primes. Okay, well, this implies that there exists an m that's greater than n, and m is a prime, and m plus 2 is a prime. Which means, okay, if n and n plus 2 are twin primes, then there's another number, m, that's greater than it, and such that it is also twin primes. The idea is as follows. If n is a twin prime, then there's a larger twin prime, which is another way of saying there's an infinite number of twin primes. Okay, question, is this statement true or false? It's still an open math problem. It's believed to be true, but it's still an open math problem. Okay. 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 Okay, great. Now, what I want to do is, so now that we have the concept of predicate, domain of discourse, I want to go on and talk about this from the categorical point of view. Namely, I want to talk about operations. Okay, I want to talk about operations on these things. And the idea is as follows. The idea is as follows. Good. Now that we have all these examples of predicates, and you can see what there's a million examples of predicates. You should open up any logic book and really get a feel for it. But now that let's put it categorically, okay? And so we start off as follows. We let x bar be a set of variables. Okay? And then we form the following thing. Predicate, instead of proposition, we call them predicate, but they have variables. Let's not make that capital. X bar. Okay, so let's say what these are. These are predicates, okay? The objects are predicates that have free variables in X bar, as much as you want. Now, let's just show what the arrows are. Q of X bar implies R of X bar. If whenever this is true for its variables, this is true for its variables, for the same variables. Okay, so this forms a category. It's just like proposition. In fact, a prop is simply pred of the empty set. It has no free variables. There are no free variables. Okay, so this is called predicates. Very nice. This is a category of predicates. It's, again, a pre-order category. It's very nice. It's very useful, and we get over all the same things that we had before. So let's go through it. You have, how do we do it on this side or that side? Do it this way. Pred of X bar goes through a diagonal to pred of X bar squared. Okay, that means pairs of predicates. Okay, and this takes, you know, Q to Q comma Q. Okay, and of course this has a left adjoint and a right adjoint. Okay, and this is or this is and. So everything works exactly like it worked in for prop. It works here also. Let's just do this. You have pred of x bar. Okay. Pred of x bar. Okay. And so this is open bracket and q of x bar, and this is q of x bar, internal arrow, open bracket. Main point, left adjoint, right adjoint. Okay, and what else? Pred of x bar, I think one of those is an op, pred, here's a not of x bar, here's a not, okay, and this is an injunction, at least in Boolean, the Boolean case, this is an equivalence of categories. Very nice. Okay, so everything that worked for propositions works for predicates also. Main point, and is a product or is a coproduct. Everything works out perfectly. Great, but there's more. We have to deal with the quantifiers, okay? So let's deal with the quantifiers, and that's the main subject of this. So consider the following category. Damn. Pred of x bar comma y. So this is those predicates which have variables from either here or y. So y is just another variable, okay? And then we have pred of x bar, and that's very nice. And it goes as follows. Let's say you have a typical variable, typical predicate in here. We'll call it q, and it uses variables from x bar, and it uses a variable y. Well, then we can quantify over y, and so we get there exists a y of q of x bar comma y. So we quantify it. Now here x bar is free, y is free. Here y is bound. We have only x bar is free, so it's in here. So basically, what this quantifier does is it takes something in here and it takes it into there. Okay, but we have to show that it respects functoriality. In other words, if you have two things here, okay, the quantifier respects it. It does. Okay, we'll leave that alone. But there's another quantifier that you can use here also, and that's this. For all y, q of x bar comma y. Quantify, universal quantifier over the y, and again, this only has free variables in here, and so this is a functor from here to there. These two quantifiers are functors from here to here. And again, you have to show that this is functorial. But not only are these functors, we have to show they're adjoint functors, okay? And so the rest of this is doing that. I just want to give away the story right away. I want to tell over the story very quickly. Okay, I'm doing it differently, the opposite way of that it's in the book, but that's okay. Okay, this is delta. Okay, so here's the idea. Take a formula that's here and just look. A predicate in here has variables that are in x bar. Well, it also has variables that are in x bar or y. So it's like including it. Okay? It's like an inclusion. This really has nothing There's nothing special, but it's called diagonal because it's kind of what it's true. If it's true over here, then it's true for all possible y over there also. Anyways, and now we have the quantifiers. Okay, and so this goes this way, and this is for all y, and this goes like this, and this goes like that. So those are the quantifiers. Now, it takes a little time to see it, and it's a little effort. I'd like to go through it, at least most of the details, before we do that. So, but this is the result of that, and you'll see we get a lot of results out of this quantification. Again, this all goes back to Levere. Quantifiers as adjoints, that goes back to Levere. Okay? So, in order to do this, in order to see that quantifiers are adjoints, what you have to do is as follows. You have to go back to what we did in chapter 4. We did it in chapter 4. Take a function from s to t. Okay? Some of this we did in chapter 1. Some of this goes back to chapter 4, in the middle of chapter 4. Take a function from s to t. So then we can look at the power function of t and the power set of t and the power set of s. Okay, and we have this f minus 1 of x, f minus 1. So that takes a subset of t back to this is called the preimage functor. I'm sorry, this is called the preimage functor, and it takes a subset of t to those things that go to that t. Okay, so that's called the preimage functor. Great. This has two adjoints. And I think it goes like this. And we say this is the exists in f, and this is for all f. And just make sure I didn't mess up. Yeah, okay. Okay, so I'd like to show you what this is. Let x be, so I want to show you what these are. Let x be a subset of s. Okay, so that's an element in here. I want to show you what so this is it, but let's just write this in. This is a subset of x. Where does it go to? And the answer is it goes to the set of y. So there's going to be a subset of t, set of y such that there is, okay, you can write that as upside down e, there is an x member of x, that's a capital X, that's a capital X, okay, such that f of x equals y. Okay, so it goes forward, but it goes forward. Pretty much goes forward. Okay, great. Let's do it. This one's a little bit more mysterious. This one's a little bit more mysterious. So this is equal to, I'm sorry, for all f of x, that's a capital X, this is equal to those y such that, okay, for all s member of s, if f of s is equal to y, then s is a member of x. Okay, so let's just say what this says. This says, look, if everything, the only things that are going to get into y are those things from s of x. Now, I have to show you, there's a very pretty picture on 239 that shows exactly how this works and shows you exactly what this means, these adjunctions. Okay, so it's right there. There's lots of pretty pictures. This whole section is full of pretty geometry. Great. So this works for any s and t. Any set maps, you have this adjunction. Now, what I'd like to do is work with this, but not with just any function, but you'll see a particular function. So let's say we understand this. I'm sorry, this has image. This is called the preimage. This is called the This is called the direct image. This is called the inverse image. Okay, great. But, so, this is true for all possibilities, for all functions, any type of functions, but we're interested in one function in particular. We're interested in this, pi, which goes from s cross t to t. Okay, I'll show you why we're interested in this in a minute, but now let's do this. You have the power of s cross t. You have the power of t, okay, and this goes the other way. So maybe I should have drawn it the other way. Okay, fine, it doesn't matter. So this becomes pi minus 1 of t, of things, okay. I'm sorry, this is the projection function. Takes pairs of things, just projects it to the t, okay? Just think for a second what this function does, the inverse. It takes a subset of t and it does every single s that would do that. So it takes a subset of t and it gives you the entire s that does that. Guess what? This has two adjoints, okay? We call them existential pi and for all pi. Okay, and they're adjoints. Very nice. Okay, now what these functions actually do, if you follow what did for f, or an arbitrary f, you get that. And on page 220, I have very pretty pictures of what this looks like. So I'd like to show you what the pictures are, but you have to stare at the pictures for a while to see how these two things are adjoint. This shows you how they're adjoint. This shows you how they're defined. The point is as follows. The way to think of this is s cross t. So this is s and this is t. Sorry, the other way. This is t, this is s. Okay, and your projection function, it just does on t. So if you have something like this, that subset, then it's going to go to that subset, okay? And we show you how it works. Okay, so it just projects onto one direction, and that's exactly what this is. Okay, and the idea is as follows, and let's explain what the purpose is. Remember we were dealing with predicates of x bar comma y, and then predicates of just x. And the way to think of this is you're somehow, here you're dealing with two things, s and t, and here you're projecting onto it. You're only thinking about some of the variables. You're not just thinking about the other variables. Okay? This codiagonal is really doing this. And this codiagonal has two adjoints, and you get that. Okay, so again, it's not details. There's not a lot of details. The point is there's an intuition, okay? And the intuition follows from the pretty pictures. So you can follow the pretty pictures and you see it. Okay, great. Okay, so now some results. Okay, so not only is it are they adjoints, but they go as follows. We have a generalized De Morgan's law that goes as follows. I'll just do it the way it's in the book. P of x bar comma y is isomorphic to there exists a y such that not p of x bar comma y. Okay, the idea is as follows. Before we even get to this, the idea is as follows. Just like and is a left adjoint. Let's just make sure we have that right. I'm sorry. Just like or is a right adjoint, so too existential is a right adjoint. Okay? And is a left adjoint, so too universal is a left adjoint, is a right adjoint. Okay, so we had the pictures here again. Okay, the way to think of it is universal is just a giant and. It's just a giant and. And the idea is as follows. If I say everybody is happy, that says this guy's happy, and this guy's happy, and this guy's happy, and this guy's happy, and this guy's happy. Keyword, the word and over and over and over. If I say there is someone in the room who's happy, there is someone in the room that's happy, well, that's just a bunch of ors. He's happy, or she's happy, or she's happy, or she's happy, or she's happy. So universal quantifier is a generalization of conjunction. Existential quantifiers is a generalization of disjunction or. Okay? Great. Okay, so what did the regular De Morgan's rule say? It said if it's false that, I don't know, P and Q, that's equivalent to, okay, not P or not Q. Okay, sorry, not Q. Okay. We saw this already, but again, the idea is this is a bunch of, this is an ends, these are ors, okay? And so we generalize this to here. Instead of having two ands, we have universal over all members of the domain of discourse, okay? And instead of having two ors, we have over all members of it, of the domain of discourse, and we have the not in front of it. Okay, so this is one generalized De Morgan's rule. The other generalized De Morgan's rule is the exact opposite. So for example, P of X comma Y is the same thing as, okay, for all Y not P of X bar comma Y. And that goes along with the other thing, with the other De Morgan's laws. De Morgan's laws come in pairs. This is a generalized De Morgan's law. Let's just do it in terms of people being happy, let's say. If I say it's false that everyone is happy, that's the same thing as saying there exists someone who's not happy. Okay, and if I say, go the back, okay, I said it's the same thing. Okay, let's do another one. If it's false that there's someone who's happy, that means everybody is not happy. If it's false that there's someone who is happy, that means everyone is not happy. Works out. Okay, great. How do you prove it? You prove it very nicely with the same type of diagrams we had before. Okay, page 222, same type of diagrams. You have these adjunctions, okay, and here you have the adjunctions. You're going to have predicates of X, predicates of XY, and the opposite, okay? And it's the same thing, but instead of the ands and ors, you have the universal things, and here you have nots. So it's exactly the same proof as before, but before we were dealing with ands and ors, and here we're dealing with universal quantifiers and existential quantifiers. The main point is, we don't care. It's adjoint functors. Okay, and the proof goes again, the same thing. There's one map like this, and so any left adjoint to that would go fine with that. Okay, great. Some other theorems go as follows. Something like this. For all X, P of X and Q of X is logically equivalent to for all X, P of X, and, so that's one thing, for all X, Q of X. Okay, and the reason why this is true, another reason why this is true is, look, this is just a bunch of ands, and each and you have two of them. Well, you just rearrange all your ands, and you have this. Now, it's not necessarily true Okay, I don't want to erase it. It's not, if this was an or and this is an or, it won't work out. It would be true one way, but not the other way. Okay, so what it's saying is the generalized and is a good homomorphism with the regular and. That's it. Okay, and the same thing about this for all x, p of x or q of x is the same as there exists an x, p of x, or there exists an x, q of x. And that takes care of that. Okay, again, how do you prove it? Same type of diagram here. Okay, and basically here you're using not only, before we use that not as an equivalence, here we're using left adjoints and right adjoints. So what we're saying is that the adjoints get along, the universal adjoints are nice homomorphisms with the ands. The existential adjoints are nice, get along nicely with the ors. Okay, it's the same type of proof. And then there's an exercise which is very, very similar. Okay, I want to finish with two. So that's basically categorical logic. Basically, you have these categories, and you have lots of different operations on them, and you have lots of different properties of the things and properties of these functors, and you show how they respect a lot of information. Okay, two things. One is there's a relationship between logic and sets. They seem very similar. Okay, and the idea is as follows. This is P and Q. Well, that gets very well along with, you could have a set A and you can have a set B, and then you can take the intersection of that. Okay, and a lot of properties that are true here are true here. A lot of properties that are true here are true here. And the reason is very simple, is because this is equal to those x such that x is a member of A, and x is a member of B. So basically, the definition of this intersection uses the logic. So I'm not saying anything complicated here. I'm just saying there's a relationship between what we saw with operations on logic and operations in sets, and you can see why. Let's just do another one. P or Q corresponds to A union B, which is equal to x such that x is a member of A or x is a member of B. Okay, and finally, not P is going to correspond to A complement, which is equal to those x such that it's false that x is a member of A. Okay. Again, the main point is that these operations in sets are defined by logic, therefore they have similar properties. And this is where we get into Boolean algebras and stuff like that. We'll see more of this at the end of chapter 6 and get into this. This is also the beginning of something called topos theory, which we're going to see in chapter 9, etc. So main point is sets and logic are intimately related. Okay, great. I'd like to finish off by reading something to you, the last paragraph of this section. It goes as follows. It's from the book, and what I'm trying to do is I'm trying to show why categorical logic is so nice. Again, logic has been around for 2,500 years. Categorical logic is a nice addition to that study, and I just want to read to you why. Before we close this mini course, it pays to meditate on what was accomplished here. What was gained by presenting logic from a categorical point of view? ? Our goal here was not simply to show that logic can be done in the language of category theory. Rather, our goal was to demonstrate several important ideas. So we're going to list off 3 ideas that are very important that we did with this categorical logic. And again, it shows the beauty of category theory. It shows the power of category category theory. It shows the versatility that it can be talking about a lot of different things. But let's go through it very carefully, these three things. We showed that logic is united with other fields that we met on these pages. The unity, the book is called Unifying Concepts, so we should talk about unity. The unity comes from the fact that logic employs the same tools of products, coproducts, functoriality, equivalence, adjunction that are used in other areas. Okay, so we're up to page 223 of the book. We saw lots and lots of examples of products, coproducts, functoriality, etc., etc. It's nice to see them, that they show up in logic also. Great. Number 2, we showed that the various logical operations do not stand alone. Category theory shows that the operations are intimately connected to each other and can be defined in terms of each other with universal properties. So the very fact that some are left adjoint to the diagonal, or and is right adjoint to logical implication. Okay, sometimes it's an equivalence of categories, sometimes it's an adjunction of categories, but the main thing is all these operations are defined in terms of each other. Okay, so that shows that there's something inherent about them. It's not just, we made up these operations. Okay, last point. We showed that many of the truths of propositional and predicate logic are simple consequences of the universal properties of the operations. A logical statement is not true because it seems true. Rather, the statement has to be true because of the way the operations are defined in terms of other operations. So restatement of the same thing. Next, last line. Categorical logic is a wonderful modern contribution to the ancient field of logic. Anyways, categorical logic is a beautiful topic. We're going to see more of it when we talk about HOTT, homotopy type theory. We're going to see more of it when we talk about topos theory. We'll see more of it in the end of chapter 6. We're going to talk a lot about duality theory. We'll see some more parts of logic. Anyways, have a wonderful day.